Hello, class. So this is the third video on section 4.6. In the previous videos, we talked about Rogers theorem, and we did an example working with that, and the mean value theorem, and we did an example working with that. In this video, we're going to do a sort of easy application of the mean value theorem. Okay, so let's go through this example. So the Jamaican sprinter Usain Bolt set a world record of 9.58 seconds in the 100-meter dash in the summer of 2009. So that's the statement. What is the question? Did his speed ever exceed 1/2 kilometers per hour during the race? So at first you look at this problem and I would think, I don't really know how to do this. So we kind of have to use a little bit of intuition and think, well, we've been talking about Rogers theorem and the mean value theorem. So if there's no other way or other approach we can think of, I would say we should try something like that. Okay. So how could we use the mean value theorem? So let's say we let f of t be the position of the runner, of Usain Bolt. So this person is running on the line, right, which means that we can definitely model this with just a function, right? So you remember, as we said in class, all of the modeling we've been doing is one-dimensional motion, right? So think of motion on the line, so we can definitely model it with a function of one variable. Right? So let f of t be the position of the runner, right? Which means if we have just with this f as we've defined it, so the starting line, or when t is 0 seconds, right, before he starts running, the starting line would be at distance of 0, right, or position of 0, and then after 9.8 seconds, oops, oh yeah, 9.58, sorry. After 9.58 seconds, well, we know that the Usain Bolt had ran 100 meters. So basically the position of the runner now is 100. So I'm just defining this function. This is the position of the runner, and we have this condition that f of 0 equals 0, and f of 9.58 is 100. Just with the input being the time and with the information we have. Now, if we want to use the mean value theorem, we need two things here. We need our function to be continuous on the interval 0 to 9.58 and differentiable on that interval. Now, we don't have any more information in this problem, but can we assume that this function is continuous? So certainly the position is continuous. Right? It doesn't matter how Usain Bolt runs, whether he runs forwards or backwards, or how fast he runs. There's definitely it's definitely in a continuous matter, right? He can't teleport from one place to another. So if you were just drawing the position of Usain Bolt, it would have to be, you would have to draw it without lifting your pencil, unless he could teleport, which we know he can't. So for sure, we can say that f of t is continuous. Now, why can we say that it is differentiable? Well, remember that differentiable is the same for us as saying that it is smooth, right? There's no sharp edges, and there's no places where the slope is vertical. Well, what would need to happen for this graph to have a sharp edge? Well, let's see what would need to happen if we just draw here a quick sketch of this function f. What does it mean for f to have a sharp edge? What would this mean? This would mean that Usain Bolt is running. So this is t. It's called t naught. This is the t-axis. This is the f of t-axis. What would this mean? That means that Usain Bolt was running, and then at time t naught, he stopped for some reason, and then started running the opposite way. And that's what it would mean if for this function to have a sharp edge, as I drew here. Of course, it is safe to assume that Usain Bolt is not going to do that. Right? Usain Bolt is not actually going to stop and then start running in the opposite direction, because again, he's running as fast as he can in the positive direction towards the end line. So we can assume that there's no sharp edges. Similarly, we can assume that nothing like this happens where the slope is vertical, because what would that mean? That would mean that the speed of Usain Bolt, right, if it's approaching something that's vertical, the speed would have to be very fast, like approaching infinity. And I'm pretty sure that Usain Bolt doesn't run at a speed that's getting really close to infinity. Right? So it's safe to assume that there's no sharp edges, right? So no sharp edges, and there's no places where the slope starts to look like a vertical slope. Those are the only things that would make our function not differentiable, right? So we can assume here then that our function is differentiable. Now that we have this, we can just end up and use the mean value theorem. So let's go to another page. So by the mean value theorem, and remember I said that I was going to use MTB for mean value theorem. We know that there exists a value, let's call it C, in the interval. So what's our interval that we're working on? 0, 9.58, such that let's write it in another color, such that f prime of C equals, well, the slope of the secant line between these 2 points. So what's the slope of the secant line? Well, let's write it like this first. F of 9.8, sorry, keep writing 9.8. F of 9.58 minus f of 0 over 9.58 minus 0. That's what the mean value theorem says. Okay, so if we simplify this, f prime of C equals, so f of 9.58, remember that was the position when he reaches the end line, right? So he ran 100 meters, which would be 100. F of 0, again, f is a position. At time 0, he's still at the start line, so that's just 0 over 9.58 minus 0, which is 100 divided by 9.58. The only thing is that this is in meters per second, right? Our position was given in meters and our time in seconds. The question was asking whether the speed ever exceeded 1/2 kilometers per hour. So we have to change this to kilometers per hour. And then I'm just going to do this here just for as a review of how to do unit conversions. So what we're going to do is we're going to multiply by, so this is meters and this is seconds. We're going to multiply by 1,000 meters because that's the same as 1 kilometer. So here, this is the same as multiplying as 1, right? Because 1 kilometer is the same as 1,000 meters. So this is how changing the unit works. We multiply by 1, basically doing the conversion. We also want to convert seconds to hours, right? So there's 60 seconds in 1 hour. And notice that I could have as well written 1 hour divided by 60 seconds, but I write it like this because I want the seconds and the seconds to cancel. I want the meters and the meters to cancel, right? So that's why I write it in this particular way. So if we simplify all this, so let's see, we have 3 zeros that cancel with the 3 zeros on the bottom. So this ends up being 6 divided by 9.58 kilometers per hour, which is, of course, greater than 1/2, right? Kilometers per hour. Now, this is just, this here is just the speed. This here is f prime of C. Now, the problem was asking about speed. Okay? But again, we have to remember what is f prime. Well, f prime is giving us velocity, right? So notice that this here is velocity. But if we're going in the positive direction, velocity is the same as speed, right? Remember, speed is just the absolute value of velocity. So for us, this is speed. So what did we find? Well, f prime of, there is a C in the interval 0 to 9.58, such that f prime of C equals 6 divided by 9.58 kilometers per hour. And remembering that f prime of C is just the velocity at time C, then we get our answer. There is a time, specifically time C, where the speed of Usain Bolt actually exceeded 1/2 kilometers per hour. Okay. So it's just a nice example of where we can see how we can derive these functions, and as we've done in other examples, just using reasonable assumptions, we can see that this function that we defined, being position, was actually reasonable to assume that it was both continuous and differentiable. And then after that, it's just using the mean value theorem to get our answer.